Right, welcome back to the second part of the Doppler effect video. We just do a quick recap. We were talking about the effect, what happens to waves, of the observation of waves by observers. If there's relative motion between the source of the waves and the observers. So in this case, we've got an ambulance moving towards this person here. This person would now observe a higher frequency of these waves. If it was sound, they would hear a higher pitch. If it was light, they would see a higher frequency. And the same for the person behind, except now they would observe a longer frequency, right? And that's the Doppler effect, the change in the perceived or observed frequency due to the relative motion of either the source or the observer. All right, now this is a blank slide of the PowerPoint. The next slide has got everything filled in. If you understand this, once you can use it as a revision tool. If you understand it, you should be able to fill this in from memory. But anyway, let me go through and explain it. So what I've got on the left here is the basic scenario where you've got a source of waves. Here the waves moving out. V stands for the speed at which these waves are moving. And here's an observer, and at this point the observer and the object are not moving. There's no relative motion between them. So if that was the case, then the source frequency, the frequency emitted by the source, which we call Fs, that's the frequency that these waves are being given out by, is going to be exactly the same as the frequency that is observed by the observer. Right? Those two frequencies will be the same. If we therefore change that little formula around and divide the observed frequency by the source frequency, since those two values are equal, that ratio will be equal to 1. Now, you may not be clear at this point why we're doing that, but you'll see it leads us to an equation which turns out to be quite useful. Since 1 is equal to anything divided by itself, if we, and you'll see why in a minute, if we decided to divide the speed of these waves by themselves, then that would also give us 1. And so that would be a little formula. Now, you might think it's a bit pointless at this point, but you'll see when we introduce some motion, it becomes useful. So at the moment, because everybody's stationary and there's no relative movement, the frequency of the observed by the observer and the frequency emitted by the source are equal. So you divide them, you get 1, and that's also equal to the speed of the wave divided by itself. Okay, so let's change up the situation a bit. Let's say that there is relative movement between the source and the observer, where either the source is moving towards the observer, shown by this red arrow, or the observer is moving towards the source, shown by this red arrow. Now, either of these situations will have exactly the same effect. They will cause the perceived frequency observed by the observer to be higher than what it actually is. Now, look at what that's done to the formula. We had a formula where we had FO over Fs was equal to V over V. But now the observed frequency is going to be higher than the actual frequency of the source. So this ratio, FO over Fs, is going to be greater than 1, because FO, the observed frequency, is going to be greater than the actual frequency given out by the source. Well, if this is increased, then to keep this ratio equal, we need to increase what was on top on the right hand side. Now, if you remember, if we go back here, we had V over V. FO over Fs was equal to V over V. So if we go back to this top bit of the fraction has to increase, because we know that FO is increased. And we could increase that by adding to it the speed of the observer. If the observer was moving to the left at a certain speed, we're going to call that V0. That's the speed of the observer. Now, if you added that to the speed of the actual waves themselves, that would have the effect of increasing the ratio, which is what we want. The other thing we could do to increase this fraction is we could reduce the bottom. Now, if you reduce the bottom, it would have the same effect. It would also increase the ratio, which is what we need to do, because we know that FO is bigger than Fs. And so FO over Fs must be bigger than 1. The number at the top is going to be bigger than the number at this bottom. So we could either add something to the top, increase the top, or we could subtract something on the bottom. Now, in this case, since Fs is on the bottom, it might be sensible to subtract the velocity of the source from the bottom. You know, the velocity of the source. The source is, we said in this case, moving to the right with a velocity of Vs. So if we subtracted that from the velocity of the actual waves on the bottom of the fraction, that would have a similar effect of increasing this ratio. And that's what we need to do, because we know that FO needs to be bigger than FS, so this ratio needs to be bigger than 1. Now it turns out that if you do it like this, then the calculations work, and you will actually get an observed frequency that if you did this in real life and measured it, it would be the frequency that you measure. Right? So what you now need to remember is that if either the object or the source of the waves or the observer are moving towards each other, either of those is going to increase the frequency, and the way to represent that in the formula is to have this ratio of FO over Fs, and you want to increase the top of it. So you're going to add the observer's velocity to the top, or you could subtract, well, if both of them are moving, then you must also subtract the speed of the source from. Both of those will have the effect of increasing the ratio, and if they're both moving, then both of those need to be done. This needs to be added and this needs to be subtracted, and you will find that the ratio actually mirrors exactly what you would measure if you measured those two frequencies. The easy way to remember this is, I think, just to remember that if they're moving towards each other, it doesn't matter who's moving, but if they're moving towards each other, they're going to increase the fraction. To increase the fraction, you need to add something on the top and minus on the bottom. Since observer frequency is on the top, we add the velocity of the observer on the top. And since the source frequency is on the bottom, we minus the source frequency from the bottom. Now that to me makes sense, and that's the way I remember it. If that doesn't work for you and you want to find a different way of remembering it, that's fine. Our notes do it slightly differently. Our notes choose one direction as positive and one direction as negative. And if you're happier with that explanation, then work with that. It doesn't matter which way you do it, as long as you show it correctly in the formula. Right, so this is a situation where there's relative motion towards each other. The frequency observed must increase, and so we add the velocity of the object, of the observer on the top, and we minus the velocity of the source at the bottom. Obviously, if either of these is 0, then that just falls away. That section of the formula just falls away, and it makes no difference to the observed frequency. Right. Well, conversely, you can imagine what's going to happen if either of the objects are moving away from each other. If both of them are moving away, then we've got a source velocity and we've got an observer velocity, but they are moving away from each other. We know that that must decrease the frequency, so the observed frequency must be less than the source frequency. And in order to, if this observed frequency is less than the source frequency, then this ratio is going to be smaller than 1, because this is going to be a small number and this is going to be a big number. Well, how do we make this smaller than it was? We can subtract something from it. Because the observed frequency is on the top of the fraction, we would subtract the observer's velocity. So the velocity of the observer would be subtracted from the velocity of the waves. Don't forget that V stands for the velocity of the waves. VO is the velocity of the observer. If the source is moving, then the source's velocity must also decrease the observed frequency, and so the source velocity, in order to decrease this ratio, must be added to the bottom. And all you have to remember is if things are moving away, you must decrease the observed frequency, and you want to decrease this ratio. You would decrease the ratio by subtracting something on top and adding something on the bottom. Right, we'll do a couple of examples in a minute, which hopefully will make it a little bit clearer. It's a bit theoretical at the moment, I realize that. But if they're moving away, the frequency must decrease and the ratio must decrease. And I think that's quite a simple way to remember it. Obviously, you can combine these two. And we know that if the movement is towards, then the ratio or the observed frequency must increase. If the movement is away, then the observed frequency or the ratio must decrease, which means in our formula, any motion that is going to increase the fraction I've colored in red, the observer frequency would increase. Any motion that would reduce the observed frequency I've colored in green, and that would mean that the observed frequency would decrease. I know my notation here might confuse you a little bit, but this formula mustn't confuse you, because this is exactly how the formula is quoted in the data